Oh, very nice. Welcome to the Banauli Film City developed by Mr. Prakash of Banauli Village, sursand. And I am Fake Lorentz and Fitzgerald. And today here I am going to discuss about the consequences of Lorentz transformation like length contraction and time dilation. And in this I will discuss what is proper length and proper time. So let's start. First, we see the Lorentz Fitzgerald length contraction. Lorentz Fitzgerald length contraction. A body moving with a velocity v relative to an observer appears to the observer to be contracted in length in the direction of motion by a factor under root 1 minus v square by c square. Let us prove it. Consider a rod flashing along x dash axis of a moving frame of reference S dash. Let x sub 1 dash and x sub 2 dash be the coordinates of the ends of the rod as seen by an observer in S dash frame. Then the length of the rod as observed from S dash is L sub 0 equals to x sub 2 dash minus x 1 x sub 1 dash. Here L sub 0 is the rod's length as measured in a frame reference in which it is at rest, that is in frame S dash. Now suppose another observer, that is which is in the frame S, measures the length of a rod from a stationary frame of reference S relative to which the rod is moving with the velocity v, that is because frame S dash is moving. If he records the coordinates of the ends of the rod as x sub 1 and x sub 2 at a time t, the rod appears to him as having a length of L equals to x sub 2 minus x sub 1. So from the Lorentz transformation for a given value of t, we have x2 dash equals to x sub 2 minus v into t divided by under root 1 minus v square by c square, and x sub 1 dash equals to x sub 1 minus v into t divided by under root 1 minus v square by c square. Hence the L sub 0 equals to x2 dash minus x sub 1 dash equals to x sub 2 minus x sub 1 divided by under root 1 minus v square by c square equals to L by under root 1 minus v square by c square. So v square by c square, and we get equals to L by under root 1 minus v square by c square. Hence we get L equals to L sub 0 open braces under root 1 minus v square by c square close braces. This is represented by equation 2. Here L sub 0 represents proper length and L represents the contracted length, that is length measured by the observer in frame S. The equation shows that to the stationary observer In fairness, the rod placed in the moving frame S dash appears to be constructed by a factor of under root 1 minus v square by c square. This contraction occurs in the direction of relative motion if v is parallel to x, the y and z dimensions of the rod are same in both s, same s and same s dash. Now we will discuss about the time dilation due to Lorentz transformation. So let's see what is time dilation. Time intervals are also affected by relative motion. A clock moving with velocity v with respect to an observer appears to have slowed down by a factor of under root 1 minus v square by c square. Then when at rest with respect to him. Suppose a clock is placed at the point x dash in the moving plane S dash. An observer is S dash time step path with two ticks at time t sub 1 dash and t sub 2 dash. The time interval between the ticks adjusts from S dash is t sub 0 equals to t sub 2 dash minus t sub 1 dash. Here t sub 0 is the interval time interval as measured in a frame in which the clock is at rest. Now suppose another observer measures the time interval with his own clock between the same two ticks from a stationary frame of reference S dash frame S relative to which the clock in frame S dash is moving with velocity v. If he records the ticks at time t sub 1 and t sub 2, the time interval appears to him as t equals to t sub 2 minus t sub 1. T sub 1, that is t equals to t sub 2 minus t sub 1. Now we know that from the Lorentz transformation for a fixed value of x dash, t sub 2 equals to t sub 2 dash plus t sub 2 equals to t equal to t sub 2 equals to t sub 2 dash plus x dash into v by c square. T sub 2 equals to t2 sub dash plus open braces x dash v by c square close braces divided by under root 1 minus v square by c square. And t sub 1 equals to t sub 1 dash plus x open braces x dash v by c square close braces divided by under root 1 minus v square by c square. Hence time interval t equals to t sub 2 minus t sub 1 equals to t sub 2 dash minus t sub 1 dash divided by under root 1 minus v square by c square, or t equals to t sub 0 divided by under root 1 minus v square by c square. This is equation 3. This equation shows that to the stationary observer in
frame S, the time interval appears to be lengthened by a factor 1 by under root 1 minus v square by c square. Thus, a stationary clock measures a longer time interval between events occurring in moving frame of reference than does a clock in the moving frame. In other words, a moving clock appears to be slowed down to a stationary observer. This phenomenon is known as
the time dilation. Now, if then the velocity between a frame is equal to the velocity of light c, that is v equals to c, then time t tends
to infinity. It means that a clock moving with
velocity moving with the speed of light will appear to be completely stopped to a stationary observer. Now we see the definition of proper time interval. The proper time interval is the time interval measured by a clock attached to the observed body. In the above example, T sub 0 is the proper time interval and C is non-proper time interval. So we can say that because frame X that is moving, and in this frame measured time is proper time interval, and frame X this is not moving, so that time interval is known as non-proper time interval. Now let's see the experimental verification of time dilation. First, mean is on detail. Direct experimental evidence for time dilation has been found in cosmic rays. Certain particles called mean mesons are created by fast cosmic ray particles at a height of about 10 kilometers from the surface of the Earth and reach the Earth in a large number. They have a typical speed of 2.994 into 10 to the power 8 meters per second, which is 0.5 of the speed of light speed. Further, a mean meson is found to have an average lifetime of 2 into 10 to the power minus 6 seconds, after which it decays into an electron. Thus, in its lifetime, a mean meson can travel a distance of only 2.994 into 10 to the power 8 meters per second into 2 into 10 to the power minus 6 seconds, equivalent to 600 meters or 0.6 kilometers. Then how do mean mesons travel a distance of 10 kilometers to reach the Earth? The answer is supplied by the special theory of, the answer is verified by the special theory of relativity. The mean meson has a lifetime of t sub 0, 2 into 10 to the power minus 6 seconds in its own finite reference. In the observer's frame of reference on the Earth, however, the lifetime is lengthened owing to the relative motion to the value c given by 3 equals to t sub 0 divided by under root 1 minus v square by c square equals to 3 into 10 to the power minus 6 divided by under root 1 minus the square of 0.998 equals to 3 into 10 to the power minus 6 divided by 0.063 equivalent to 3.17 into 10 to the power minus 5. In this lifetime is a 0.998 that is equals to 2.7 power 8 meter per second can travel a distance equals to 3.994 into 10 to the power 8 meter per second into 3.17 into 10 to the power minus 5 seconds, equivalent to 19,500 meters or 9.5 kilometers. Hence, despite their brief lifetime, short lifetime, it is possible for the mesons to reach the ground from the large altitude at which they are actually formed. So, we have seen the experimental verification of time dilation in example mean meson decay. So here we have discussed the proper time interval or proper length, and I think you are enjoying this video. Written Banauli theme city developed by Mr. Jayaprakash Ji of Banauli Hill Station. I am highly indebted to Mr. Jayaprakash Ji who gave me chance to start with visiting the Banauli theme fashionable theme city Banauli. So with this I would like to in this movie at this class. Thank you very much watching my this movie.